Hi everyone. In this video, we are going to have a look at how to graph cubics from the general form. So this is what the general form looks like. So it's not factorized. It's not in turning point form, in transformation form. So we've just got f of x equals a x cubed plus b x squared plus c x plus d, with a not equal to 0. So it's okay if this term or this term or this term is missing, but you need at least to have an x cubed in it, obviously. So that will only happen if a is not equal to 0. Cool. Okay, so let's have a look at the other steps which we would use in order to solve such a problem or graph such a problem. So first of all, we have to factorize. If we don't factorize it, we won't be able to work out the zeros. If we can't work out the zeros, then we can't graph it. So what are the steps for factorization? First of all, we need to look for common factors. Let's get the mouse out of the way. Then we need to use the factor theorem to find one of the factors of the cubic. Once we've got one of the factors, we can then use polynomial division in order to find the other factor, and we can then factorize using trinomial factorization. We can work out the other factors from there. And I should just point out that look, maybe it won't work. Maybe we can't find any factors. Now, in a test situation, you would be able to find them if it tells you to find them. It's too. Otherwise, it would be a long waste of time in a test. But generally speaking, that if you're in a real world situation, then there may not be any. So, for example, the graph might look like this. So there is one x-intercept, but there's no other x-intercept. So how would you be able to solve that? Well, you would only be able to graph it if you knew the turning points, so you knew where to go back and forth. So you can only do that if you've done some work in calculus to figure out those turning points. So yeah, it might be partially factorizable, but not completely. Okay, so we'll assume that it is fully factorizable though, because otherwise it's not as fun. What do we do after we've factorized it? We can use those factors to work out the x-intercepts. We can then work out the y-intercepts. We can then work out the end behavior. So once we've done the factorization step, the rest of it is effectively from intercept form as usual. Although, of course, the y-intercept might be just a little bit more easier to find if it's in general form, because if I go back to the general form there, oops, not far enough, then that would be 0, that would be 0, that would be 0. So clearly the y-intercept would just be, not c in this case, d, the constant term. So keep that in mind. Okay, so that's basically what we're going to do now with an example. So let me go to the example here. F of x equals negative 2x cubed minus 18x squared minus 52x minus 48, and we have to form a graph from that. Now you might see what I've got here is I've split this page into 4 little quadrants here. This is just so that I can get all the working out to fit into this one section. Maybe it might need to be 2 sections, I'm not too sure. So let's just see how we go. I'll just zoom up on this first section. And if you remember, step 1 was to do the factorization. And in the factorization steps, what we had to do is find common factor first of all, and then go from there. So part A was, so this is step 1, factorization. Part A was to find a common factor. And if you have a look at the equation, we have a negative 2 here, negative 18 here, negative 52, and a negative 48. So there's definitely a common factor of 2 here. And I can see that taking out the negative as well is going to be helpful. So not only will I take out a common factor of 2, but I'll make it a common factor of negative 2. So I'll just zoom up again. F of x equals negative 2 outside of, and that leaves me with x cubed and positive 9x squared, positive 26x, and then positive 24, plus 24. Okay, so that becomes our slightly factorized expression. And now I'm going to try and factorize the inside. And to do that, we're going to use the factor theorem. So let's just remind you about the factor theorem. I'll just go to the previous page to do that. So we're looking at the factor theorem here. The factor theorem simply says that if I have a value a substituted in for x, and the polynomial, in this case it's f of x, results in 0, then it must be that x minus a is a factor. Okay, it also is true that if x minus a is a factor, then f of a will be equal to 0. So I can put an arrow on either side of that equal sign there to say it goes both ways. Okay, so that's the factor theorem in a nutshell. If I can find a number that when I substitute for x, the whole function results in 0, it must be a factor. So that's handy to know. So we start looking for solutions. So what have we got first of all? I tend to go for negatives and then go from there. So f of negative 1 is equal to negative 2 outside of negative 1 cubed plus 9 times negative 1 squared plus 26 times negative 1 plus 24. And then we evaluate that a little bit. So negative 1 cubed is negative 1. 9 times negative 1 squared is 9. So this gives me 8. And I can see from the last two terms that's not going to give me 0. So f of minus 1 is not going to equal 0. So x plus 1 is not a factor. Okay, remember we've got to reverse the sign there. Null factor law kind of stuff. Okay, so I won't go any further. Similarly, I can now look at f of 1, and I can see that's going to give me negative 2 outside of 1 cubed plus 9 times 1 squared plus 26 times 1 plus 24. And again, I've got, so it's all positive, 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 positive. It's not going to give me 0. So that's no good as well. So where do I go to from here? Just as a little aside, if I have a look at the equation here, in order for this to be factorizable, all of the numbers, x minus 1, x plus 2, x minus 3, whatever the factors happen to be, they're going to have to multiply together to give me 24. If I just go back to the general form again, so there's the general form there, that number there. When I factorize it, I'm going to get like x minus a, x, well, not these a, b's, and c's, but x minus something, x minus something, x minus something. The something times something times something has to multiply together to give me d. So keeping that in mind, I just need to really consider the factors of 24. Now, in this instance, it's not that helpful. As you'll see, the factors of 24 are multitudinous. 1 would be a factor, 2 would be a factor, 3 would be a factor, 4 would be a factor. Don't have to worry about 5, but 6. Don't have to worry about 7, but 8. Not 9, not 10, not 11, 12, and 24. They're all factors, but also so are the negatives. So there's actually quite a heap of factors, but it does mean that there are a few I could skip. You could imagine that if this number here was 7, that'd be cool because it'd be like only 1 and 7, negative 1 or negative 7 are the only ones I have to consider. But that's no good in this instance. But we'll just keep on going down the line. So we've done 1 and negative 1. So now let's do negative 2 and see how we go. So f of negative 2 is equal to negative 2 times negative 2 cubed plus 9 times negative 2 squared plus 26 times negative 2 plus 24. And we'll evaluate that a bit, I think. Negative 2 outside, well, negative 2 cubed is negative 8. Negative 2 squared is 4, positive 4. So that gives me plus 36. 9 fours are 36. Minus 52, 26 times negative 2. and then plus 24. So that gives me, okay, so that gives me, if I look at the positives, that's 36 and 24, which makes 60, and minus 8 minus 52 gives me negative 60. So this whole thing's going to give me 0 inside the brackets, and negative 2 times 0 is 0. So that's equal to 0, so therefore x. Now let me have a look. It's minus 2, that worked, so x plus 2 is a factor. Now, I should say that I could keep on going. I could go f of 2, and then f of minus 3, f of 3, f of minus 4, f of 4, and I could keep going and draw out all the factors. It is a bit of a long, laborious method of doing that, and if there happens to be a factor there which is like 2x plus 1, you'll miss it if you keep doing that, but it is possible to do that. A better next step, which is part C, which I'll do in the next little box down here, is to use polynomial division. So just to remind you how polynomial division works, it's effectively the box method in reverse. There are other polynomial division methods. There's synthetic division and polynomial long division, and you can find YouTube videos or ask me if you want to see that in action. But here's the reverse box method. So we start off by saying, okay, when I multiply, if x plus 2 is one of the factors, then the other factor, which must go with that one to give me a cubic, must be a quadratic. So x squared, so an ax squared plus bx plus c form. Okay, so there's 3 terms there. So what I'm going to do is I'm going to draw 3 sets of boxes. Like so. And this is where my terms will go. So on the left-hand side, I write down the parts of the factor I just worked out, like so. Plus, in the first and last box, I'm going to put the first and last term. Now, I don't have to worry about the negative 2. I'm just factorizing the inside here. So I'm going to draw into, I'll use a different color now that I'm going inside the box. I'm going to draw x cubed here, and I'm going to draw 24 here, plus 24 to be precise. Now, what I do is I fill out my box method, the rest of the stuff as we go along. So I go, x times what would give me x cubed? And the answer is x squared times x gives me x cubed. Then I multiply these 2 out to give me this box here. 2 times x squared is positive 2x squared. Now have a look at what I need. I need 9x squared. And so I've got 2x squared already. So I need to add another 7x squared. That gives me my 9x squared. X times what equals 7x squared? X times 7x. So I've got a positive 7x here. 7x times x is 7x squared. 7x times 2 is positive 14x. Okay, that's all good so far. I've got 26x that I need. I've got 14 already accounted for, so that's 12x left. X times what will give me 12x? X times 12. Now that's all my boxes filled out, but I also have to just check 2 times 12 does equal 24. It gives me that number that's already in there, so I'm pretty confident I didn't make any mistakes. So this is one factor, this is the other factor. So I can say, therefore, f of x is equal to negative 2 outside of x plus 2 times x squared plus 7x plus 12. Brilliant. All I have to do is factorize this bit here, which I can do. You can use your favorite method, box method, cross method, or any other method that you use. For simple ones like this, I simply say, are there 2 numbers I can multiply to give me 12 that will that'll add together to give me 7, like so. So that would be 4 and 3, right? 4 3s are 12 and 4 plus 3 is 7. So I can say that's equal to negative 2, x plus 2, x plus 3, x plus 4. And now it is factorized. Okay, so what do we do now? We've got a factorized expression here, and we are now interested in ensuring that we've got enough information to graph. So we move on to step 2. So step 1, factorization is done. Step 2 is the x-intercepts. Okay, so number 2, x-intercepts, let y equals 0. So what does that mean? It means that -2 outside of, what were the factors again? X plus 2, x plus 3, x plus 4. Okay, so x plus 2, x plus 3, x plus 4 is equal to 0. So y was equal to -2 outside of blah, blah, blah. So therefore, if we set y equal to 0, then all of that is equal to 0. And now, by the null factor law, each of those factors here, here, and here must be set equal to 0. So that will give us x equals -2, x equals -3, x equals -4. That's nice. What else we got? We also need the y-intercepts. Zoom up a little bit. Let x equals 0. So this is where, if you know the original function, is no need to be too laborious about it. So here's the original function here. When x is equal to 0, that goes, that goes, that goes. So I'm left with -48. So rather than, wasting time calculating that, I can just go 0, -48 from the original function. No dramas doing that at all. And number 4 is the end behavior. So as x approaches -infinity, what's y doing? So I'd probably do this from factor form, but you could do it from, look, I'd probably do it from here, but I can easily do it from here as well. So again, the -48 doesn't make much of a difference when x is huge, so we just have a look here. Negative infinity. Okay, so when negative cubed is negative, negative times a negative is positive. So this will be positive. A positive minus a negative squared that's going to be positive there. So that'll be a negative minus more, because that negative will change it. And then realistically, we've got a -52 times a negative. It's going to give us a positive here, but it's far outweighed by these two. In fact, you should argue that it's the x cubed that really affects the behavior at x equals -infinity. Even squaring a big number is going to be nowhere near as big as cubing a really big number. So realistically, we can say that since x is when x is approaching -infinity, the cube of it's going to be negative. We're multiplying by a negative, and it's becoming positive. And so we can say that as x approaches -infinity, y is positive, and as x approaches positive infinity, what's happening? We have, look again, just looking at the x cubed term, x is positive, cube a positive, and you get a positive multiplied by a negative, and you get negative. So y is negative. Okay, so there you go. So there's the other critical points. Well, there's all the critical points in this particular box. We've got -2, 0, -3, 0, -4, 0, and 0, -48 being the intercepts. And then we know the end behavior. And again, turning points do not need to be calculated. At this stage, you need to know a little bit of calculus in order to determine that with accuracy. So in this one here, let's draw the graph. So The y-intercept was at negative 48. I'm not going to get this to scale again, so I'm not even going to try this time. There's my x-axis. There's my y-axis. My 4 points are negative 2, negative 3, negative 4. So I'll put negative 4 there, which means that negative 2 would be about there, and negative 3 is about in the middle. The y-intercept is at negative 48. So I'll just put it down as far as I can, but it's just going to be not to scale at all. And then we are starting off when x is equal to negative infinity, y is positive, so we're starting up here somewhere. And then when x is positive infinity, y is negative, so we're going to end down there. So it's going to be something along the lines of, I'll draw it in red, coming up here and around and up and down, and then through minus 48 and keeps on going. Like so. Again, that wasn't the best graph. It's a bit slanted off to the side there, but it gives you a fairly decent impression with what you're going to do. Let's confirm this in Desmos. So we've got f of x equals, let's have a look now. We'll turn that one off and we'll go y is equal to negative 2x cubed. What was it? Negative 2x cubed minus 18x squared minus 52x minus 48. And that's what it looks like. I'll just zoom that out. So it goes, I'll better zoom it in so you can see the x-intercept. So it goes down to minus 4, down and up to minus 3, up and then down to minus 2, and then keeps on shooting down to negative 48, as you can see just there. So that's the graph, and that does confirm more or less what my graphs look like here. And that's basically the end of it. So you've now got the ability to draw a graph from any possible combination. So base graph, which has been transformed, you're right to go. If it's in intercept form to start with, you're right to go. And if it's in general form, you know to factorize first and then do it from intercept form. So that should be it for how to graph a cubic given the function. In the next video, we'll have a look at how do you graph how do you work out the function given the graph. But that will do for today. Bye.